Well, ladies and gentlemen, we've got a real doozy for you here today. We're going to talk about horizontal stretching and compressing. Now, this whole thing about stretching and compressing can kind of be summarized with one word, and we call it a dilation. So sometimes today, if you hear me say horizontal dilation, I'm just kind of shortening up this whole title today of horizontal stretching and compressing. Now, everything we did last night with the vertical stretching and compressing, or vertical dilations, could be summarized in this picture right here. We talked about what if we put a multiple of 2 in front of f of x, and we talked about how that's going to make the graph taller. Or we said, what if we put a multiple of 0.5 in front of f of x, and then we said it makes the graph a little shorter, a little more compact and closer to the x-axis. Well, today we're going to put our multiples on the inside of the function. So basically, look at these green functions. Compare this yesterday's green function to today's green function. Notice how the multiple of 2 is on the inside. And what that does is it makes the graph more narrow. It didn't make it any taller. You'll notice the max is just as high as it used to be, and the relative min is just as low as it used to be when you compare it to the original blue function, but it makes it more narrow. By comparison or contrast, if we put 0.5 as a multiple on the inside of the parentheses, in other words, the actions on the inside today, the graph is going to be wider. It's got the same relative max, we've got the same relative min, it's just everything's wider and stretched out. So our mega question today is, what effect will replacing y equals f of x with y equals f of kx have? And so we're going to study that effect. Here's going to be probably our hardest slide of the night, and it's going to be a little discovery exercise. So let's talk about first, we're just going to work on graphing this function right here. So I'm using my calculator, I'm typing it into y equals, and then I'm going to just jot down the table of values. Now we do know from studying our shifts earlier that this V-shaped graph is moving to the right 2 units, and then it's going to move up 3 units. But just to get a real precise set of points, I'm going to use the table feature of my calculator. And here's what my calculator spit out. And let's see here. And what I'm going to do here is I'm going to transfer all of these points onto my graph here in a split second. And we expect to see a nice V graph with a vertex at 2, 3. So that's our original function. Now, here's where we really want to start investigating and diving in. So now, what happens if I replace that function with this new function, f of 2x? Now, the key here is we're substituting the 2x in for x. So first of all, I'm going to rewrite the new equation. And again, I'll repeat, I'm taking this 2x and I'm substituting it for the original x. And here's what my new equation looks like. Be the absolute value of 2x minus 2, close the absolute values, plus 3. So that's what my substitution looks like. Now here's maybe the most interesting part, is look at what happens to my table of values. And again, we can even do these by hand. You could either substitute this equation into y equals on the calculator, or we could just evaluate these by hand. You know, substitute a -1. And let's see. Negative 2 minus 2 is negative 4. The absolute value is positive 4. Plus 3 is going to give me 7. And if I substitute a 0, I get a 5. If I substitute a 1, I get a 3. If I substitute a 2, I get a 5. If I substitute a 3, I get a 7. And I think that's going to be enough points to plot. And I'm going to go ahead and I'm going to plot those real quick here. And that would put me at negative 1, 7, 0, 5. Ooh, interesting. That's it. Very interesting. I got the same y-intercept as I had earlier. 1, 3. It looks like my relative min got shifted over 1 unit. Then 2, 5, and 3, 7. Okay, right there. So here's what's happening. Just like we saw on the last slide, my graph is significantly more narrow. And so I'm just going to jot that down. The blue graph, when I substituted 2x for x, I got a lot more narrow. All right, I think it's time for me to pull out one more color here. Let's see, which color am I thinking? Yeah, we'll try this one right here. So first thing I'm going to do is I'm going to substitute. I'm going to write a new equation. I'm going to substitute the 0.5x in for the original x. And it's minus 2, close the absolute values, plus 3. And this time I'm going to get a little sneaky. When I do my table of values, I'm only going to substitute even numbers for x. And the reason I'm doing that is because I'm multiplying by 0.5, so even numbers are the easiest ones to work with. And when I substitute a negative 2, I got a 6. And when I substitute a 0, I got a 5. When I substituted a 2, I got a 4. When I substituted a 4, I got a 3. And when I substituted a 6, I got a 4. So I'm going to go ahead and I'm going to plot those points. Let's see, negative 2, 6 right here. and 0. Ooh, look at that. Same y-intercept, all same thing again. Then 2 comma 4 and 4 comma 3 right there. So my relative min got shifted to the right this time, and then 6 comma 4 right back up here. So maybe I should have done at 8 I would have probably gotten a 6. So I'll draw it right through there. We'll draw this side right through there. And this graph got a lot wider. So today, the theme is we're not making the graphs taller or shorter. What we're doing is we're either making them more narrow or making them wider. One thing there, do notice that the y-intercept stayed the same for all of those functions. Okay, so let's get right down to it. What's the number one thing we need to know tonight? Okay, here's what it boils down to. If we take f of x and we replace it with y equals f of kx, the value of k only affects who? The x coordinate. Okay? In other words, each x coordinate is divided by, and that's going to sound a little weird, but it's going to come to life here in the next couple of examples. But just keep telling yourself each x coordinate is divided by the value of k. Let's take a look, and let's kind of summarize what we saw in the last slide there. If k is greater than 1, the effect will be a horizontal compression. And what I mean by compression is it made the graph more narrow. However, if k is somewhere between 0 and 1, maybe k is equal to 1/2 or 1/3 or 2/5 or something like that, the effect will be a horizontal stretch. And what we mean by a stretch in this case is it's going to be wider. So the whole idea of a compression and stretch take on a little different meaning today because we're speaking horizontally instead of vertically. Okay, one more slide before we get into some real live examples that we're going to see on tomorrow's sheet and in future quizzes and tests. But I want to talk about recognizing the difference between a vertical dilation, which is what we did yesterday, versus a horizontal dilation, which is what we're doing today. So yesterday we notice where the k was yesterday compared to where it is today. Yesterday the k was on the outside, today it's on the inside. So let's see what we're going to say. Yesterday the action, so to speak, was on the outside. And what that did is that caused a vertical dilation. Compare that to today where the action's on the inside, and when it's on the inside, the effect is a horizontal dilation. Now, algebraically speaking, think about what we did yesterday. K was a multiple of f of x, and what I mean by that is the value of k eventually gets distributed. So that's the magical math property that we were using yesterday. The value of k gets distributed through the function f of x. Now today it's a totally different ballgame. Today, since the k is on the inside, we're going to say the quantity kx gets substituted. And we were using that term quite a bit on the last slide. Gets substituted for every x that was in the original function f of x. So the big key algebraically is yesterday was distribution, whereas today is substitution. Okay, we're going to put it all together, and here's some good examples of some questions we're going to see tomorrow. So let's start with this. Let's take the original f of x. We're going to replace it with y equals f of 3x. The effect will be a what? Now here, what we want to say to ourselves is that the k value in this case is a 3. And that's bigger than 1, isn't it? So the effect is a horizontal compression by a factor of 3. And the effect is that's going to make my graph a lot more narrow than it originally was. Now how about example number 2? What if we replace f of x with f of 1/4 x? Now here we're saying k is equal to 1/4, which is less than 1. The effect will be a horizontal stretch by a factor of 1/4. And remember, we defined a stretch as something that makes the graph wider today. Alright, this next one, they said there's going to be a compression by a factor of 5. So that's going to be f of 5x. In the next example, we said there's a stretch by a factor of 2/3. So that would be f of 2/3 times x. Okay, so what if we knew that 6 comma 4 was a point that lies on y equals f of x? Our job is to try to identify a point that lies on the following functions. Now I want you to go back a couple of slides and remember the slide where we asked you what's the number one thing we need to know today. And we said that when the action's on the inside, okay, it only affects the x-coordinate. It's not going to affect the y-coordinate at all. So for instance, in every answer I have for all of these problems, my y-coordinate's going to stay 4. Only the 6 is going to change today. And how does that 6 change? Well, the key is, and it sounds weird, but we're dividing by the value of k. So, and just keep reminding yourself, divide, divide, divide. So what we're going to do is we're going to take the 6, we're going to divide it by 2, because what's happening is we're making the graph more narrow, okay? And it's going to be 3 comma 4. And just think, remember, anytime that k is greater than 1, we're making the graph more narrow, and that convinces me why I need to divide by 2. Okay, now again, let's divide the 6 by 1/2, and feel free to use your calculator. 6 divided by 0.5, that's going to actually turn into a 12. Now, sometimes it sounds better this way. Instead of saying dividing by 1/2, that's equivalent to saying multiply by 2. Either way, you're going to come up with a 12. And the effect is we're making the graph wider. The third example, we're going to divide by 4. 6 divided by 4, you could call it 6/4, or even better yet, reduce it to 3/2. Y-coordinate stays the same, and we just made the graph more narrow. Okay, and the last one, we could say take the 6 divided by 1/4, and again, we could rely on the calculator, and the calculator should say 24, or we could say 6 times 4. Either way, you're going to get 24, and now the graph is much wider. Okay, our next set of problems here, they said that the x-intercept of a function is 9. Can we find the x-intercept of the following functions? And remember, our couple of themes, the number one thing, and maybe even the only thing we really need to know today, is that we're dividing the pre-existing x-intercept by this factor of 3. So we're dividing, and only the x value is changing. The y value, which in this case is 0, this ordered pair would be 9 comma 0. That's not going to change. So let's see what we got here. If I take my 9 and I divide by 3, my new x-intercept is going to be 3. Let's take that 9, divide by 1/3, and that's going to be a new x-intercept of 27. Let's see. Now, how about this number? If I have a 4/3, is that making my graph wider or more narrow? And that's just kind of a question for fun. Well, we could say k is equal to 4/3, which is greater than 1, so we're making a new function, a new graph that's more narrow. Either way, all we have to do to answer this question is take the 9, divide it by 4/3, and that's going to give me a new x-intercept of 27/4. Or you could turn that into a some kind of decimal if you want, and it doesn't matter as long as your answer is equivalent to 27/4. And for our very last one, we take the 9, we divide it by 1/6, which is the same thing as multiplying by 6, and you end up with a new x-intercept of 54. Okay, now in this case they're giving us a domain, and this function has a domain with an x-min of -2 and an x-max of 8, and they want me to identify the new domain of the following functions. Again, these types of these horizontal dilations only affect the domain. It wouldn't have any impact at all in the range, so it wouldn't even make sense to ask that question perhaps. But anyway, let's go ahead and we'll start dividing. And let's see, start with your x-min divided by 2, and the new x-min is -1. Or we'll take the x-max divided by 2, and we'll get a new x-max of 4. So there's your new domain. Let's try the next one. Start with your min divided by 1/2, and that's going to be -4. Or we could take the x-max of 8 divided by 1/2, and that would be a new x-max of 16. Okay, here we go. They've given us the original f of x equation, and we want to write a new equation that represents f of 3x. And there was a word we used earlier tonight, and that fancy word was substitution. So the theme here is substitution. We're going to substitute a 3x in for all these x's. So the first one's going to start off like, we'll say, well, f of 3x is equal to, now notice all the parentheses I'm going to use here. And I'm going to encourage you to use as many parentheses as possible. And it's, let's see, we'll start to clean these up. That's going to become 9x squared minus 18x plus 10. And that's all there is to it, because there's no more like terms to combine. I just had to evaluate each term individually. Now this next one's going to be a little bit trickier, and the reason it's a hair trickier is because of this negative sign. But watch how I handle it. So in this case, if I said I'm going to substitute a 3x, the negative goes outside, then the parenthesis, then the 3x. Okay? And the location, keeping this negative on the outside is going to be huge. And just continue to substitute 3x for each of the x's. clean these up a touch here. So it's going to be negative, and then we square the 3x to make it 9x squared plus 12x minus 6, and we're all done. Now in this question, and watch how the focus is on algebraically accomplishing this. They want me to prove algebraically that the two following functions have the same y-intercept. And what I did is I just grabbed the first example from that last slide. Here's the original, and here's what f of 3x looks like. And what we're trying to prove here is that the y values don't change, or they're not affected. It's only the x values that change. Now recall from earlier discussions that a y-intercept means we're going to substitute a 0 for the x values, each one. And so on this first example, we'll say f of 0 equals 0 squared minus 6 times 0 plus 10. And that turns out to be 0 minus 0 plus 10. So this function has a y-intercept of 10. And then we'll try the same process over here. F of 3 times 0 equals 9 times 0 squared minus 18 times 0. And I have to say, I think 0 is like my favorite number in the world to evaluate without a calculator, because I just get 0 minus 0 plus 10, which ends up being a same y-intercept of 10. So all that work of showing your substitution and then just evaluating each term is our way of proving algebraically that they have the same y-intercept. Okay, we're going to finish the night off with a little bit of graphing, and so they've given me a graph of f of x already, and that's what we see right here, this little backwards check mark. And they want me to graph f of 2x. Now remember, in this particular case, before we jump in, we know that the value of k is a 2, and because that's greater than 1, that's going to be a vertical compression, and it's going to make my graph more narrow. It's a little bit counterintuitive because you think like when you multiply something by 2 it makes it wider, but remember we're not multiplying, we're actually dividing by 2 here today is our theme. Now what I'm going to do is I'm going to identify these 3 points. I'm going to call them A, B, and C. And what you notice, point A has a ordered pair of -4, 6. Now what happens if I divide the x-coordinate by 2, that creates a new point. I'm going to call it A prime. And the new point is -2, 6. Notice we divided the x-coordinate by 2, but we didn't change the y. And so -2, 6 would be right here. And I'm going to label that A prime. Okay, B, let's see. Right now that's 2, 2. And because, let's see, if I divide the x-coordinate by 2, I get 1, 2. Whoa, 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 whoa. That should be a 2. There we go. 1, 2 is going to be right there. And we'll call that B prime. Notice how everything's getting closer to the y-axis, aka more narrow. And then C is at 4, 5. By the time I divide the x-coordinate by 2, that's 2, 5. And let's see, 2, 5 right there, that's C prime. So notice my new graph, significantly more narrow than the original one. But however, compare the maximums. The maximum, these two maximum points have the same height, and the two minimum points have the same height, and even the C and the C prime, they have the same height, again, just more narrow. Almost the identical problem. We're still starting off with that same function of f right here, and I'm going to start off with the same idea of labeling my A, my B, and my C. You know, if you feel comfortable, you know, if you're doing the work in your head, I'm really okay with that. The only reason I'm writing it out is just so you can kind of see what thoughts are floating through my head as I go through this. So point A is -4, 6. I'm dividing the x-coordinate by 1/2, which makes it -8, 6. So that new point is going to be right here. We'll call that A prime. Let's see, B we said was 2, 2. I'm going to divide the x-coordinate by 1/2, and that makes it 4, 2. So now we're right here. We'll call that B prime. And remember, point C was at 4, 5. If I divide the x-coordinate by 1/2, that makes it 8, 5. And that's going to slide me right there, C prime. So my new graph goes from here all the way to here, all the way to there. And again, it's much, much wider for f of 1/2 x. Alright, last example of the night, and we're going to practice graphing a quadratic function. And so let's see. First things first, in order to graph x squared minus 2x, you know, we could prove what the x-intercepts are algebraically. We could do the y-intercepts algebraically and all that jazz. Tonight, our goal is, though, to focus on, what impact is this 1/3 having. So I'm going to use the calculator, and the calculator's giving me a table of values that looks like this. So we go 2, 0, 3, 3, 4, 8. And what I'm going to do is I'm going to go ahead and plot those points and get this original parabola on paper. And now that I've got that there on my graph paper, now I'm really going to turn my attention to what impact does f of 1/3 x have on that function. Now remember, we could say that my k value here is a 1/3, and because that's smaller than 1, we're expecting this to make the graph a lot wider. And the one thing I'm going to do is I'm basically going to recopy this table, but as I'm recopying it, I'm going to divide every x coordinate by 1/3. And so my new table of values is, for instance, this -2 is now going to be -6, 8. And then it goes -3, 3. 0 stays 0. The 1 turns into a 3. The 2 turns into a 6. The 3 turns into a 9. And that's about all that I'm going to have room for on my graph. So now I'm going to go ahead and I'm going to plot those new points. -6, 8. Yep, wider. Let's see, -3, 3. And 0, 0 stays that. 3, -1. And then 6, 0. And then 9, 3. And that's about, yeah, you can see that's all I had room for. Interestingly enough, the y-intercept is the same, and the height of my relative mins, the height is -1 on both of these. It's just the x-coordinate that changed. So remember this, when the action's on the inside, it only affects the x-coordinate, and the value of k divides that x-coordinate. So it's all about dividing tomorrow.